One final thing I want to talk about with these harmonic oscillator wave functions is this is the first example that we've come across in this class of the phenomenon in quantum mechanics known as tunneling. And this is that a particle can exist in a quantum system where it shouldn't be possible to exist in classical mechanics. And we see this evidenced in this quantum system on these edges over here. Now, according to a classical picture, the particle shouldn't have enough energy to ever go past this sort of barrier here. Right, the spring can only stretch so far. There's only so much energy in the system to let it stretch. But according to quantum mechanics, if we look at the probability distributions in particular, right, there is some finite probability. It's not very large, but there is some probability that it can go past where classical behavior would predict that it can. And so we didn't see this with the particle in a box because the potentials were infinite. But if we did this instead, right, if we did a particle in a box where the box wasn't actually infinite, right, so if this was a finite box instead of an infinite box, the wave functions you get look something like this. So we see the same phenomenon where we have the wave function extends past where you would expect the particle to be able to go. And so this is the idea of tunneling. Now, this is relevant in actual real-world applications. The first example that comes to mind for me is the tunneling electron microscope. We take advantage of the fact that this can happen and intentionally cause tunneling to happen. And so this tunneling has a specific probability, a specific chance to happen. And so what happens in an STM, scanning tunneling electron microscope, is that we have a very thin tip here that's charged. So it has excess electrons on it, so it's negatively charged. And then we have a surface that's positively charged. So the electrons want to go to this positive surface that we're trying to image with our microscope. But we keep them far enough apart that the electron can't go. But as we move the tip closer, normally they'd have to be in contact for the electrons to start flowing, but they'll start tunneling through this classically forbidden barrier and make it to the positive end, and we can control, and that the amount that it tunnels, the current that you get, depends on this distance here. And so we rely on tunneling to tell us the distance. And so we take advantage of the fact that this is happening and use it to do electron microscopy, which is really neat.